Well, in this chapter and in this lecture, we'll be talking about the details that underlie a lot of the material we talked about in the previous lecture covering Chapter 18. That is, the details that are related to the movement of solute and solvent within the kidney. And we're doing this primarily not to just cover renal physiology yet again, but to address the concept of balance, both for electrolytes and fluid. That is, how does the kidney function in terms of balancing fluid intake with fluid loss and electrolyte intake with electrolyte loss? So with that, let's talk about the concept of balance. To maintain homeostasis, what comes into the body must eventually be used or secreted. That is, we expect the input and the output ultimately to be balanced. And of course, it's not just balancing input and output, but allowing for the fact that some materials get used up, that is, they get utilized. In addition, there's a certain amount of production. Some of the water that we eliminate actually is produced by metabolism. So to be in balance, input and production has to equal utilization and output. And renal function, of course, as we talked about, it's one of the earliest slides in the last lecture, is involved in solute and water balance, that is, solute and solvent balance. It regulates fluid and electrolyte composition of the plasma. It regulates water, sodium, potassium, calcium, as well as pH, therefore acid-base balance, specifically in that case, a couple of other electrolytes, hydrogen ions and bicarbonate ions. So let's look at the various types of exchanges that affect plasma content. Well, first of all, we ingest substances. Of course, they end up in the digestive tract, and we haven't talked about that yet, but it's fairly common knowledge, and most of you would already have sufficient background to realize that, of course, this is going to lead to absorption of materials from the GI tract. Now, some of the material is going to be excreted, but in terms of fluids and electrolytes, this is minimal. Feces, of course, is primarily elimination of solid material. So we have ingestion and absorption. The water, electrolytes, etc., get absorbed into the plasma and interstitial fluid, that is the extracellular fluid compartment. There is some exchange with cells, both material moving into cells as well as material leaving cells. Also, extracellular connective tissue, such as bone. Some materials may be incorporated there and stay there. There may be some exchange going on. There can be other losses, such as sweating, hemorrhage, respiration. These, of course, affecting primarily fluid, but some of it the electrolytes as well. Sweat, of course, contains a fair amount of electrolyte. And then, of course, what we saw in renal physiology, filtration, reabsorption, and secretion. And this, of course, ultimately leads material to the lumen of the renal tubules where it's excreted into the urine. So there's a lot of movement to and fro among various organs and body fluid compartments that are involved in influencing plasma content. It's important to keep in mind here that that's ultimately what we're concerned with, is the volume and chemistry of the plasma. So with that, since plasma is solute in water, we need to look at solute and water balance. The idea of balance, again, is that solutes and water enter and exit the plasma at the same rate if they are in balance. Therefore, the quantity, the amount of water, and the amount of different solutes, therefore their concentrations. If water volume and solute volume stay the same, then the concentration of the solute stays the same. If you have a state of positive balance, what happens there is that solute or water enter the plasma at a greater rate than exiting, and therefore the quantity increases. Negative balance is when solute or water exit the plasma at greater rates than they enter, in which case the quantity decreases. And the idea there is to maintain balance. We're generally fluctuating between some minor negative balance and minor positive balance. You go out for a vigorous run, you end up in a state of negative balance. And when you're replenishing the fluid, rather than coming back to achieve perfect balance, you may end up over-consuming fluid for a while until you get into positive balance. But then you're going to eliminate that extra fluid until you get back to a balanced state. So keep in mind that these are not absolutes, that you can't be in, you have to be in balance all the time. The body is obviously trying to achieve balance, but it's going through states of negative and positive balance from time to time. So water balance. Amount of water taken in as well as that metabolically produced. Again, when cells engage in metabolism, they produce CO2 and H2O. They produce water. And that those two sources have to equal water output and water used. So intake comes from gastrointestinal tract as well as I said, metabolism. Output, well, kidneys, a lot of it, a little bit in the gastrointestinal tract. There is some water in the feces, sweating. And then what's called insensible loss. A certain amount of moisture that you lose from your exhaled air as you realize on a cold day and you can see your breath forming water vapor, as well as just a certain amount of water loss through the skin. And I'm not talking about sweat. Even just sitting and resting without sweating, there's still a certain amount of water loss that occurs through the skin. And because it's not measurable, we call it insensible. So the factors that affect water balance. Well, we ingest about 2.2 liters a day. And, of course, through the digestive tract. We've talked about the fact already that we don't eliminate very much water through our feces. Very little loss through the digestive tract. Most of it, of course, is being lost through the urine. So we have, about 2 liters being absorbed. And some of that, of course, is going to end up being secreted. We have digestive enzymes and other fluids, and we'll talk about that again in the digestive system. But keep in mind there is a certain amount of fluid loss from the standpoint that the digestive tract receives fluids in the source of various secretions. But again, most of this 2 liters gets absorbed, ends up being part of the total body water. There is a small amount, about 300 mils a day of water that's actually produced by metabolism. Have a certain amount of loss or insensible loss, sweating we've talked about already. And again, our renal functions. And of course, we end up filtering out about 180 liters, but ultimately excreting only about 1.5 liters. And the outputs, we have only about total of 2.5 liters per day of output, taking all of these into account. Now that means we have perfect balance. You have, on average, drinking about 2.2 liters a day. And of course, this is something that you can control. The production due to metabolism, and then all of our losses here, these come into balance, 2.5 versus 2.5. Thing of important note here is that the kidneys can only minimize fluid loss. Intake is required in order to add fluids. And of course, for that reason, we consume a fair amount of fluid. Let's go through a review of osmosis. If you have membranes, as we do in most organs, that limit the ability of electrolytes, that is, solute, to diffuse, then water, which generally is freely capable of freely diffusing, water will diffuse down its concentration gradient. So it diffuses toward the area where there is greater solute concentration, because, of course, by definition, if there's high solute concentration, there's low water concentration. So water moves from a low solute concentration, which means it's a high water concentration, to a high solute concentration, which means a lower water concentration. Again, keeping in mind that water is solvent, and everything else, the electrolytes and everything that we're referring to, is solute. So water reabsorption follows solute reabsorption. That as solute is lost in the renal system, we have sodium that's leaving the the tubular lumen being reabsorbed, that water follows, that we've already seen that as an example. Now with osmosis, we need to think about osmolarity of fluids, which is basically, if you will, the concentration of water in those fluids. So the osmolarity of body fluids normally is about 300 milliosmoles. And there is no osmotic force for water to move between fluid compartments because, at least in a normal healthy individual, those fluid compartments are isoosmotic. When we talk about the fluid compartments, we've covered them before. It's intracellular fluid and extracellular fluid. Extracellular fluid, again, consists of the interstitial fluid, that is the fluid between the cells, and plasma. All of these compartments normally are isoosmotic, meaning that they have the same osmolarity. The kidneys compensate for any changes in the osmolarity of the extracellular fluid by regulating water reabsorption. So if somebody is sweating a lot, they're losing water, then the kidneys have to compensate by retaining water that would otherwise end up in the urine. And as we saw before, water reabsorption is passive. It's based upon the osmotic gradient that water follows solute. So in the proximal tubules, 70% of the water that was filtered out is reabsorbed, but it's not regulated. It's just following solute reabsorption, and the primary solute is sodium. So while we, in the press and information for the average person on the street about health-related issues, of course, there's always an emphasis on reducing the sodium in our diet. Sodium is a very important substance because, in this case, water reabsorption follows sodium reabsorption. The thing is that far too many people, especially in this country, consume way too much salt. They consume far more than they need for vital functions as well as enhancing water reabsorption. The distal tubules and collecting ducts, most of the remaining water, that is, we had 70% that was reabsorbed, the remaining 30%, most of that is going to be reabsorbed in the distal tubules and the collecting ducts. But this is regulated. So the proximal tubules, it wasn't regulated. In the distal tubule and collecting duct, it is regulated by ADH, which is anti-diuretic hormone. If you think about the word antidiuretic, diuresis means production of urine. So this means to fight the production of urine or counter it. Antidiuretic hormone's chemical name is vasopressin. So sodium reabsorption, which is important, of course, because it drives water reabsorption in the proximal tubule. We have sodium being transported along with glucose, and then, of course, a sodium-potassium ATPase, helping to keep the intracellular concentration of sodium here low, so that sodium is moving down its concentration gradient ultimately and ending up in the plasma. So sodium is actively transported across the basolateral membrane here, which establishes an osmotic gradient for water reabsorption. So the water will follow the sodium. We saw that on a slide in the previous chapter. So water reabsorption in the proximal tubule. As we said, it follows solute, most of which is sodium. We just talked about that. For the steps for water, and in this case, urea reabsorption, we have our sodium transport along with other solutes. We saw glucose as an example before. There are other solutes as well that can be transported. And again, the sodium-potassium exchanger. Other substances going through various pumps where they're not being co-transported with something else. But water and urea, both following the osmotic gradients that have been set up, or at least water following its osmotic gradient, urea is following its own because, of course, urea is fairly concentrated in the urine, and therefore it's just moving down its concentration gradient. But some of this is following along the movement of water. So just as water will move in response to solutes, some solutes will move in response to water. So we have here several solutes that are actively reabsorbed, increasing the osmolarity in the pure tubular fluid and plasma. And therefore, by increasing osmolarity, water is reabsorbed by osmosis. Urea, which is called a permeating solute, meaning that it can move fairly freely across membranes, is reabsorbed passively. Now, within the nephron, we haven't emphasized it much before, but there is a division. The outer part of the nephron, switch colors again here, is called the cortex. That's shown here. The inner part is called the medulla. So keep in mind that the loop of Henle plunges down into the renal medulla. So this whole area here with all these lines across it is the renal medulla. And this is important because, as we said before, the loop of Henle plays a crucial role in water reabsorption. Now, even though 70% of water was reabsorbed in the proximal tubules, much of the rest of it is going to be absorbed later on. And that is what we're dealing with in this slide here in terms of this medullary osmotic gradient. So we talked about the idea that urea is being reabsorbed from the tubule back into the tissue. So the urea that's moved back in is establishing an osmotic gradient that is shown here. And again, I encourage you to look along in your textbook, page 541, where you can see this diagram in more detail. Now, we mentioned before the normal osmolarity is 300. And right here at the boundary between the medulla and the cortex, on both sides, we have 300 milliosmoles. But as you move further down into the medulla, the osmolarity increases up to about 1,400 down here. And this is due to an accumulation of urea. So as we have our fluid coming in from the proximal tubule, coming down into the loop of Henle, and then out into the distal tubule, the osmolarity of this interstitial fluid, that is this fluid here, varies with depth. That the osmolarity is the lowest near the cortex and is greatest down near the renal pelvis, which is at the base of the renal medulla. And this gradient is critical to water reabsorption, because water is going to be moving down its osmotic gradient. So we're going to absorb a certain amount of water here in the beginning of the loop of Henle. But of course, it's only going to absorb as much water as the osmotic gradient. And we have the filtrate here, the fluid within the proximal tubule, is itself close to 300 milliosmoles. So in order to draw up more fluid, we need to have these ever-increasing steps in concentration to pull out more and more water. And it is this descending limb of the loop of Henle where water is reabsorbed. That is the water that's reabsorbed after the proximal tubule. And this sets up what we call the counter-current multiplier. Now, before I jump on to that, so we have water being reabsorbed here. This part of the tubule, the membrane here of the loop of Henle, is water permeable but impermeable to all of the solute molecules. When we go up the ascending limb of the loop of Henle toward the distal tubule, this part of the membrane is impermeable to water, but it is permeable to solutes. So we have sodium, potassium, chloride, all being transported out. Now, of course, what's happening is that by taking out water here, we are concentrating all the solutes by the time they get up here, which is going to facilitate the movement of these solute molecules out. So we refer to this as the counter-current mechanism. And this diagram is taken from another book. But if you look at it in your handout, you'll be able to see it in some detail. And what we have here is the filtrate, that is the urine that's being formed, being isoosmotic. So as I said before, this is 300 milliosmoles. and it becomes progressively more concentrated in the descending limb. And then what we have in the ascending limb is the removal of solute. Ultimately, later on here in the distal tubule and in the collecting duct, we're going to have hormones that are controlling the permeability to water. And we're going to take out the remaining water that made it through the ascending limb of the loop of Henle. And then this is ultimately fine-tuning. This part here is fine-tuning the osmolarity of urine. And we call it the counter-current multiplier because we have urine flowing through this way, or filtrate becoming urine, and blood going through the vessels surrounding this, flowing in the opposite direction. So flowing in the opposite direction, a counter-current. And what this does is this allows this concentration gradient that we've talked about to be established. And that, of course, then is going to be what permits the concentration of the urine and the reclamation of a fair amount of water. So how does it work? Again, this diagram is a bit hard to see, but if you take a look along either in your lecture handout or in the textbook, we'll try to go through this. And it's a bit artificial in that it is showing it as a step-by-step process, which is sort of what the other diagram was showing without having quite so much detail. So we end up with having our isoosmotic fluid, switch colors here, isoosmotic fluid in the in the proximal tubule coming in. And some of the water and urea coming out. And that's what's happened is over time, more, as you notice with the darkness of the color here, more and more urea is to be accumulated, which is going to facilitate the movement of more and more water progressively through this. So what this is trying to show is an increasingly concentrated fluid within the tubule as a result of this counter-current mechanism, resulting in the final situation that we see here, where we have our isoosmotic urine, which is becoming increasingly hyperosmotic until, again, it is going to reach an equilibrium with the surrounding tissue. So we had 1,400 milliosmoles out here, and of course, the urine, or the material, the filtrate that's becoming urine, is also going to reach 1,400 milliosmoles. And of course, as I said before, this helps to really concentrate solutes here, which is going to help the removal of solutes in the ascending limb of the loop of Henle. So the result of the countercurrent multiplier is that the started out with our fluid entering the loop, coming through the proximal tubule at 300 milliosmoles. As the fluid enters a descending limb, the osmolarity increases as it descends. And then in the ascending limb, the osmolarity decreases because we have these exchange mechanisms, these pumps, that are taking solute out of the urine and reabsorbing it into the blood. By the time the fluid ends up in the distal tubule, it is actually hypoosmotic. It's down to 100 milliosmoles, whereas it was 300 over here. And of course, in the surrounding tissue, the interstitial fluid here in the cortex, it's also 300. So this is also below the osmolarity of the surrounding tissue. So the cortical interstitial fluid, as I said, is 300 milliosmoles. The medullary interstitial fluid increases from the cortex to the renal pelvis. So it's less, lower osmolarity here, greater osmolarity here. And of course, this is all a result of this countercurrent multiplier. So we end up with out here, as you said, or as I said before, is more dilute urine. We've taken out so much of the solute, and this is where we're going to finish reabsorption of water, which of course is going to bring this back to something closer to 300. So let's look at water reabsorption. We've already said that 70% of water is reabsorbed in the proximal tubule. This is not regulated. 20% reabsorbed in the distal tubule. This is regulated by ADH. and another 10% absorbed in the collecting ducts. This is also regulated by ADH. So the water reabsorption going on all through here is due to regulated reabsorption that is being regulated by ADH. Now the reabsorption that's occurring is still dependent upon an osmotic gradient, and the osmotic gradient was established by the counter current multiplier. So in the distal tubules and the collecting ducts, the water reabsorption is dependent upon the osmotic gradient that was established by the counter current multiplier, and it's dependent upon the epithelium permeability to water. And this is what's regulated. ADH actually alters or regulates the permeability of the epithelium to water in these structures. And it's dependent upon what we call water channels, which are constructed of a protein called aquaporin. There are two varieties. There's aquaporin 3 and aquaporin 2. Aquaporin 3 is present in the basolateral membrane of the epithelium and the distal tubules and collecting ducts. It's always there. That's what we call constitutively active. Aquaporin 2 is present only when ADH is present in the blood. And let's take a look at how that happens. So we actually have these aquaporin 2 channels, basically. They're channels that allow water to go through, that are stored in a reserve, membrane-bound, basically stored in vesicles. And that ADH, molecules of ADH, bind to the ADH receptor. This activates a G protein, which works through adenylate cyclase, activating or increasing the concentration of cyclic AMP. And of course, just as we've seen before, cyclic AMP interacts with protein kinase A. And protein kinase A phosphorylates proteins associated with this storage mechanism for these aquaporin 2 channels, and makes them move to the membrane and insert themselves. Aquaporin 3 is here on the basolateral surface, and it is always allowing water to move out. So of course water needs to move down a concentration gradient, and by having the aquaporin 3 always there, it is allowing a certain amount of water to move down here until this, of course, becomes isoosmotic across this gradient. If you want more water to move out, you need to increase the water permeability across the apical membrane, and that's what the aquaporin 2 proteins are doing. So how is it regulated? Well, when the membrane of the distal convoluted tubule and collecting duct is impermeable to water, water can't leave the tubules. So the water stays here. We've got 100 milliosmoles, and it stays that way because there are no aquaporin channels on the apical membrane allowing water to be reabsorbed. So there is no water reabsorption, and more water is excreted in the urine. But because it's regulated, water coming in, again, about 100 milliosmoles here, but it becomes more and more concentrated, moving down through the same osmotic gradient as we saw for the loop of Henle, and working the same way as we saw in the descending loop of Henle. Water molecules continue to move out down their osmotic gradient. But of course they need those aquaporin 2 molecules to allow that to happen. So ADH stimulates the insertion of these water channels, that is the aquaporin 2, into the apical membrane. Therefore water gets reabsorbed by osmosis. And the maximum urine concentration is, of course, isoosmotic with the surrounding tissue. It would be 1400 milliosmoles. How is ADH release itself regulated? Well, it is a hormone of the posterior pituitary and is released, of course, by neurosecretory cells that originate in the hypothalamus. That is, their cell bodies are in the hypothalamus, and their axons go down into the posterior pituitary where their axon terminals release ADH. The main stimulus for release is increased osmolarity due to what we call osmoreceptors that are themselves located in the hypothalamus. Other stimuli include increased blood pressure due to the baroreceptors and increased blood volume through the volume receptors. That is, these are atrial stretch receptors. We've talked about those previously in the cardiovascular lectures. Now, there is a certain amount of what's called obligatory water loss. That is, the urine has to have a certain content of water in order to be able to eliminate it through the renal apparatus. So there's a minimum volume of water that must be excreted in the urine per day. As I said before, the maximum osmolarity of urine is 1,400 milliosmoles, and some solute must be excreted. So there is a minimum water loss of about 440 milliliters per day, and this is what's called the obligatory water loss. And this is there to help remove this solute. It's necessary to eliminate non-reabsorbed solutes. As I said before, I think in the previous lecture, that if we didn't have this, our urine might be a thick paste, very much like the excrement of birds. And in fact, the white pasty part of bird excrement is their version of urine, and it is mostly urea. But it's a very good example of what our urine would be like without this obligatory water loss. Let's take a look at glomerular filtration rate and water excretion. Now, we've seen this graph before. The GFR is normally autoregulated. That is, that the amount of filtration tends not to vary over a fairly wide pressure range. Now, of course, it does on either end of it. But between 80 and 180 millimeters of mercury, which is pretty much the normal range, and then some extra, which of course might occur during exercise in terms of the normal range and a bit of extra beyond that of blood pressure. But again, normal range within fairly normal activities such as exercise. And this is due to tubuloglomerular feedback we talked about in the last lecture. Decreases in blood pressure below that decrease glomerular filtration rate and therefore decrease the amount of water that's filtered and decrease the amount of water that's excreted. Increasing blood pressure above this autoregulatory range increases GFR and the amount of water that's filtered and the amount of water that's excreted. Take a look at sodium balance. Well, sodium is freely filtered, just as water and glucose are, but it is reabsorbed in the proximal tubule, distal tubule, and collecting duct. Sodium is not secreted. So how is sodium reabsorbed? Well, there is a regulated form of sodium reabsorption. About 70% of the sodium is reabsorbed in the proximal tubule, distal tubule, and collecting ducts. And this is regulated by two hormones, aldosterone and ANP. ANP is atrial natriuretic peptide. Called atrial because it is released by cells in the atria of the heart. Cells that when stretched actually release this substance. Now if you remember, the heart was a secondary endocrine organ, and this is why. Natriuretic because sodium, the Na part, ends up in the urine. That is the uresis, or the uretic part of the name. And what it does is that when the atria are stretched, it indicates that there is an increase in plasma volume beyond what it needs to be. So this peptide causes sodium excretion to be increased by decreasing reabsorption. And in so doing, more water is eliminated because, of course, it's following the sodium. And we'll talk a little bit more about aldosterone in a couple of minutes. So the reabsorption of sodium is regulated by aldosterone and ANP, and it's regulated at the principal cells of the distal tubule and the collecting duct. A lot of it is going on through active reabsorption due to the sodium-potassium pump at the basolateral membrane. We've seen this in many of the previous slides. Within the proximal tubule, again, we have our sodium-potassium exchange we just talked about, and this, of course, is keeping the sodium concentration within the cell low by taking sodium out. Therefore, sodium can move down its concentration gradient and does so along with other solutes. We've seen this happening, of course, with glucose through what's called a symporter because it's transporting two substances together. This, of course, is facilitated transport. And also, there are sodium proton exchangers shown here that actually proton or hydrogen ion moving down its concentration gradient, driving the transport of sodium in, and chloride moving through these junctions. So by and large, sodium reabsorption is coupled to the reabsorption of other solutes. Now this is, of course, in the proximal tubule. In the distal tubule, sodium reabsorption is coupled to the secretion of potassium and hydrogen ion. So we have the secretion of potassium, and we have the, that's not actually shown here, the secretion of hydrogen ion. I think that was similar to what we have here. It's just not shown in this particular slide. So the secretion of these two solutes drives the secretion of, the reabsorption of sodium. So sodium being reabsorbed here, and here as well. All of it that is coupled to the secretion of both of these solutes. Let's take a look at aldosterone. It increases sodium reabsorption. It's a steroid hormone. It's released from the adrenal cortex, so it is a adrenal corticosteroid. It acts on principal cells of the distal tubules and collecting ducts. And what it does is it increases the number of sodium-potassium pumps on the basolateral membrane. So let's go back to this slide. It actually increases this number of pumps and increases the number of open sodium and potassium channels on the apical membrane. Again, we'll go back. So it increases the number of open channels for both sodium and potassium. Now, of course, potassium is getting pumped in here, which is going to then move down its concentration gradient, and sodium can move down its concentration gradient, a gradient that was set up again by the same exchanger. So the open state of these channels is increased by aldosterone. So what we have in the presence of aldosterone binding to, again, remember it's a steroid, so it's lipophilic. It easily crosses the cell membrane, binds to a receptor located within the cell, and it increases the number of sodium, potassium, ATPase pumps, and it increases the number of open sodium and potassium channels here on the apical membrane. Now, aldosterone is linked to a system we've touched on before. We've talked about how renin, which is released by juxtaglomerular cells from the kidney, works on angiotensinogen. I mentioned before that angiotensinogen is a protein released by the liver. Again, renin converts angiotensinogen to angiotensin 1. Endothelial cells in capillaries throughout the body contain an enzyme called angiotensin converting enzyme. And it's abbreviated ACE. Angiotensin converting enzyme converts angiotensin 1 into angiotensin 2. Angiotensin 2 stimulates cells in the adrenal cortex, causing them to release aldosterone. In addition, angiotensin 2 also increases mean arterial pressure because there are angiotensin 2 receptors on the vascular wall, and angiotensin 2 causes that smooth muscle to constrict. So we have an increase in angiotensin 2, which causes vasoconstriction in systemic arterioles, which of course increases arterial pressure. Also stimulates aldosterone release by cells in the adrenal cortex. This increases sodium reabsorption in the late distal tubule and collecting ducts, which increases the extracellular fluid osmolarity. that increased osmolarity stimulates cells in the posterior pituitary to release antidiuretic hormone, which increases water reabsorption, again, in the late distal tubule and collecting ducts. This increases blood volume, plasma volume, which also increases mean arterial pressure. If you notice, the effect of aldosterone is itself dependent upon the effect of ADH. Aldosterone itself does not affect blood pressure. In addition, angiotensin II stimulates cells in the hypothalamus to activate thirst. Whenever you feel thirsty, it's actually because of angiotensin II stimulating this area. And this, of course, if you drink, you're consuming water. Plasma is largely water, so this, of course, is going to increase plasma volume, which is also going to increase mean arterial pressure. So as you see here, when we get into this part of renal physiology, it's almost impossible to separate cardiovascular physiology from renal physiology because the two of them are thoroughly interrelated. Let's take a little bit more of a look at renin. Well, it's a proteolytic enzyme. That is, it breaks down angiotensin I to angiotensin II. So, it lyses a protein. The stimuli for it is a decreased pressure in the afferent arteriole, increased renal sympathetic nerve activity, or decreases in sodium and chloride concentration in the distal tubule filtrate. So let's take a look at that. Mean arterial pressure goes down. The pressure within the afferent arteriole goes down. Well, of course, this will decrease filtration. So this stimulates cells in the juxtaglomerular cells to increase release of renin. Again, negative feedback is not shown here, but this, of course, goes back because it increases mean arterial pressure. It is offsetting the decrease that set it off in the first place. Decrease mean arterial pressure also will activate the baroreceptor reflex, which will increase sympathetic nerve activity, which also can stimulate renin release. And decreasing mean arterial pressure decreases glomerular filtration, which is going to decrease the concentration of both sodium and chloride in the distal tubules, which is going to alter the activity of the cells in the macula densa. By decreasing the concentration of these substances, we're also decreasing the fluid flow through the area of the macula densa. This is going to increase the secretion of paracrine, which is also going to stimulate renin release. I mentioned atrial natriuretic peptide before. Let's look at it again in a bit more detail. Excuse me. It is secreted, as I said, by atrial cells. Both, it's thought, in the right and left atria, although some people think it's more in the right atrium. These are not the same mechanism that activates the stretch receptors that we talked about before. These are cells that actually synthesize and release this peptide. So it increases glomerular filtration rate by dilating the afferent arteriole and constricting the efferent arteriole. Decreases sodium reabsorption by closing sodium channels in the apical membrane. And the overall effect is an increase in sodium excretion. Again, if you think about the idea, here's the abbreviation for sodium, Na, and uresis means urine. So we're putting more sodium in the urine. So we have here, in this flow chart, an increase in plasma volume. And this increase in plasma volume is, of course, going to stretch the walls of the atria. And this stretch of the atria is exactly the stimulus that is necessary to release atrial natriuretic peptide. It is going to do a variety of things in the kidney. It is going to dilate the afferent arterioles. And this is going to increase glomerular capillary pressure, which of course will increase glomerular filtration rate and increase sodium excretion. Well, of course, if you're increasing sodium excretion, you're going to increase water excretion. And by increasing water excretion, you're going to reduce plasma volume, which again is negative feedback. It was an increase in plasma volume that initiated this. In addition, ANP is working on the efferent arteriole to cause constriction. So if you think about it, you're constricting the vascular outflow to the glomerulus at the same time that you're dilating the inflow. So you're going to be causing basically a damming up of blood in the glomerulus, which is increasing glomerular capillary pressure. As I said a moment ago, this of course increases the filtration rate. Also, atrial natriuretic peptide decreases sodium reabsorption, which is going to increase, of course, sodium excretion. And it inhibits renin secretion, which decreases aldosterone, and that also decreases sodium reabsorption. So, as we've seen in a couple of other situations already in the kidney, some fairly complicated interrelated pathways that are involved in regulation of balance. Potassium balance. How does the kidney handle potassium ions? So first of all, in the glomerulus, potassium ions are freely filtered and they are reabsorbed in the proximal tubules. In the distal tubules and collecting ducts, potassium can be reabsorbed as well as secreted. We've already seen that in some of the slides that we showed talking about the movement of other solutes. Potassium is also secreted in the distal tubules and collecting ducts, and it is regulated here. And it is regulated primarily through aldosterone, which regulates principal cells, and as we've already seen, influences sodium-potassium exchange. So let's look at the proximal convoluted tubule for potassium reabsorption. Again, we have the lumen of the tubule here and our interstitial fluid. Of course, you've got blood flow out here in the peritubular capillaries. And there's some unknown mechanism here that is a pump that seems to be moving potassium out. And then, of course, we've got our sodium-potassium exchange here, and we have these potassium channels that is allowing potassium to move down its concentration gradient. There's also paracellular movement of calcium through these leaky junctions. In the distal convoluted tubule, potassium is secreted. So we have, again, our sodium-potassium exchanger, and this is, of course, increasing the potassium concentration in the cell, so it's moving down its concentration gradient through these membranes. So how is aldosterone, which is so important in terms of regulation of potassium, how is aldosterone itself regulated? We've already shown the renin-angiotensin-aldosterone system is part of the activation. In addition, potassium in the plasma directly stimulates aldosterone's release. As potassium increases, it stimulates the release of more aldosterone. Now, we haven't talked about calcium yet, and of course calcium is important in terms of bone. It's important for other things, obviously. We've already talked about its significance in terms of release of neurotransmitter, its significance in terms of electrical events in the heart, as well as muscle contraction. So calcium is very important, and the kidney is involved to a certain degree in calcium homeostasis. But we will talk in greater detail in other chapters on growth about calcium, because of course calcium plays such a role in bone growth. But of course we ingest calcium, comes into our digestive tract. It actually is going to be absorbed through the vitamin D3, which needs to be activated in order to allow us to absorb calcium. And then we have a certain plasma concentration of calcium. Now, calcium can move into bone through the process of calcification, which is regulated by calcitonin, and calcium can be resorbed from the bone. Notice this is not reabsorption, but the term is resorption, by parathyroid hormone and, again, vitamin D3. So calcium and bone play a very dynamic relationship in terms of bone as a repository or reservoir, storage depot, if you will, for calcium. And there's always a certain amount of calcium being laid into the bone, and a certain amount of calcium being removed from the bone. And of course, that itself needs to be in balance. Calcium is also filtered out, just as other solutes are. But it is also reabsorbed, and its reabsorption is regulated by parathyroid hormone, which increases its reabsorption, and calcitonin, which inhibits the reabsorption. So these two hormones, calcitonin and parathyroid hormone, work both in the kidneys and in bone to maintain a stable plasma concentration of calcium. So let's take a look at how the kidney handles calcium. Well, calcium is bound to carrier proteins, as well as a certain amount that is free in the plasma, but much more of it is bound to proteins. The calcium that is not bound is freely filtered at the glomerulus, whereas the calcium that's bound to the protein, of course, the protein is too large to be filtered out, so it stays within the blood supply. But of that free calcium that is freely filtered, 70% of it, again, will be reabsorbed in the proximal tubule, just as we've seen for other solutes. And then another 19 to 20% is reabsorbed in the thick ascending limbs of the loop of Henle. A smaller amount is reabsorbed in the distal tubules. And the reabsorption in the loop of Henle and the distal tubules is regulated. And let's talk about the hormones that do regulate calcium. Parathyroid hormone is released by the parathyroid glands. The stimulus for release is a decrease in the calcium concentration in the plasma. Parathyroid increases calcium reabsorption by the kidneys. We saw that on a previous slide. And stimulates the activation of calcitriol. Calcitriol is a steroid hormone derived from vitamin D3. So it stimulates calcitriol in the kidneys. This is going to stimulate resorption of bone, that is, the taking of calcium out of the bone and putting it into the plasma. So, of course, it's a way of increasing plasma calcium concentration. Stimulates the small intestine to enhance calcium absorption. The overall effect is, of course, an increase in calcium concentration in the blood. So calcitonin, it's secreted from C cells of the thyroid gland, and its release is triggered by high plasma concentration of calcium. So calcitonin is going to have the opposite effects of parathyroid hormone because it's stimulated by the opposite changes in calcium concentration. Calcitonin's action at target cells is to increase bone formation. This is a way of taking calcium out of the plasma and putting it into the bone and decreasing calcium reabsorption by the kidneys. Now the last slide comes out of a different physiology book, but I'm using it because it puts everything together that ties together renal function as well as you'll see, ultimately some cardiovascular function as well. It's hard to see on the slide. I recommend that you print off a full-page version of the slide from the handout. But let's take a look at this flow chart. It's going to take us a while to get through it because there are so many parts of it. But we start out with dehydration. That is a reduction in plasma volume. So this, of course, is shown here, a reduction of plasma volume. This also means there's a reduction in plasma or in blood pressure. This is going to be accompanied by an increase in osmolarity because by losing water, by losing solvent, there is more solute left. So already we started out with some complexity. Let's just take a look at what happens when we reduce blood volume and blood pressure. Well, first of all, reducing blood pressure is going to activate the baroreceptors, which is going to work through the cardiovascular control center in the medulla oblongata to decrease parasympathetic output to the heart. This will, of course, by decreasing parasympathetic output, we increase heart rate, and there's going to be an increase in force. This is largely due to the sympathetic effect, which we'll talk about in a moment, but this is going to be increasing cardiac output. Well, increasing cardiac output, of course, is a way of increasing blood pressure, which is going to counteract this initial stimulus. Again, activation of the baroreceptors due to this decreased blood pressure activate sympathetic nervous system, which is going to increase the force of contraction and also increase heart rate. Working in the arterioles, we're going to have vasoconstriction, which is going to increase peripheral resistance, which is going to increase blood pressure. Again, this increase in blood pressure counteracts the initial decrease that we had. Let's take a look at changing the blood volume. This is going to work on the granular cells, which is going to cause the release of renin, converting angiotensin into angiotensin 1. Angiotensin 1 is going to get converted by angiotensin converting enzyme into angiotensin 2. Angiotensin 2 is also going to constrict the arterioles to increase blood pressure. Angiotensin 2 is going to stimulate the adrenal cortex and decrease the release of aldosterone, which is going to decrease sodium reabsorption, which is going to decrease the increase in osmolarity that resulted from this decrease in blood volume. The decrease in blood volume is also going to, as well as pressure, is also going to decrease glomerular filtration rate, which is going to help conserve blood volume. Again, opposing the initial stimulus that started all of this. Increasing the osmolarity of the blood is going to stimulate osmoreceptors in the hypothalamus, which is going to, of course, stimulate the hypothalamus, causing vasopressin release from the posterior pituitary, which will work on the distal nephron to increase water reabsorption and therefore decrease osmolarity. In addition, the reduction of blood volume is going to work through atrial volume receptors, also stimulating the hypothalamus to do the very same things that the increased osmolarity itself did. There's a few other things here that I've sort of glossed over. Increasing sympathetic nerve activity also stimulates the granular cells and, of course, is going to affect glomerular filtration rate. But this slide is an excellent way of pulling all of the material together that has correlated cardiovascular control, as we have here, with the mechanisms that are affecting renal function as well as balance of both water and solutes.